Hi, thanks for giving me the chance to speak at the conference. Today I'm going to talk about our work on classical verification of quantum depth. This is a joint work with Nai-Hui, who is a professor at Rice University. You can find our work on arXiv. So in the area of demonstrating quantum advantage, our goal is to come up with a computational task or a protocol that distinguishes a quantum machine from a powerful classical computer. So a closely related problem is test of quantumness. So for this problem, there are two different settings. One is to have a classical device called verifier, talking to two devices which may share entanglement with each other, but they are not allowed to communicate once the protocol starts. By sending questions and collecting the answers from the devices to determine whether the correlation actually from players that share a certain entanglement. In a different setting, we have the purely classical verifier talking to a device, and then the goal is to determine whether the device is a quantum machine or not. So in this talk, we want to make a step further. Can we give protocols that separates a weak quantum machine from a powerful quantum computer? So the powerfulness of a quantum computer is measured through the resources it has. So what kind of resource do we care about? For space, it is known that in each setting, there are protocols for certifying the underlying Hilbert space. For depth, this is an relatively unexplored area, and will be focus of this talk. But before we dive into technical details, let us formalize what kind of computational model that we described in this talk. So motivation is the following. In the near term, we only have quantum computers that has limited quantum depth because the quantum noise is very serious and the qubits are scarce. So no fault-tolerant quantum computation can be implemented with such a small device. So in this setting, how do we leverage the power of a device with a limited quantum depth? A natural approach is to interleave a shell circuit with a powerful classical computation. So there are two different approaches that we will consider in this talk. One is called the classical quantum scheme. So in each step of the computation, we have a BPP machine that come up with a question to a shell circuit. And then by measuring the output states by the shell circuit, we obtain an outcome, a classical outcome, which is served as the input to the second step of the computation. So on the other hand, in a quantum classical hybrid computation, we can decompose a shell circuit depth D circuit into D single layer gate application. So in each layer, we have a single layer gate application. And then after the gate application is done, we measure part of the state, and then get outcomes, which is served as the input to a classical computer. And then after getting the output of the classical computer is served as the input to the second step of the computation. So with hybrid schemes in mind, we can define complexity classes BPP to the BQNC and BQNC to the BPP to include decision problem or promise problem solvable using hybrid schemes. So in this talk, I'm going to talk about protocols for classically certifying quantum depth. My work is going to consist of 3 parts. First of all, we improve the existing oracle separation results. More formally, we show that the nearest optimal separation relative to an oracle that it can be efficiently computable. So this gives the second part of our contribution, which is a 2-player game for certifying quantum depth. And the last part is of this talk will be a single device separation for QC schemes. So the first part is separation relative to efficient oracles. So the big question that we have in mind is how do we determine if a device has large quantum depth? So I would like to mention that unconditional separation seems hard because it is no easier than separating BPP from BQP, which is a major open question in theoretic quantum computer science. So in a relativized model, Nai-Hui and collaborators show that there exists an oracle, classical oracle relative to which 2D plus 1 hybrid schemes is strictly more powerful than D hybrid schemes. So the idea is the following. The task for the device to solve is a Simon's problem. So the device is going to solve the Simon's problem given access to a random shuffling of a random Simon's function. So what is a random shuffling of a random Simon's function? It is a tuple of D plus 1 functions such that the first D functions are just simply random permutations acting on a set that is exponentially larger than the domain and the range of the Simon's function. And then when you compose the D plus 1 functions in a certain order, it gives a random Simon's function. So a quantum algorithm that has sufficiently large quantum depth can simulate the Simon's oracle by querying the function in sequence, and then compute the first D functions to erase the intermediate values. This result is quite nice, but it leaves some room for improvement. So in this talk, we ask the question, can we separate a D plus constant hybrid scheme from a depth D scheme? It turns out in our paper, we show it is possible. We show that there exists a relative oracle relative to which a D plus 3 hybrid scheme is strictly more powerful than a D hybrid scheme. So the idea is the following. We use in-place permutation to avoid computation queries. And then we show that by applying a similar idea as previous paper, we show that there is no advantage over classical algorithms if the functions are not queried in order. So that shows that you must have, the device must have sufficient query depth in order to simulate the Simon's function. And then a similar result is also shown independently by Hasegawa and Lagale in a paper posted in the same day. And then we make one step further. We show that if a quantum secure pseudo-random permutation exists, then there exists efficiently computable oracles for the same separation result, which is described here. So the idea is the following. We can simulate a random Simons function using a random permutation. So we show that we can simulate a random Simons function using a random permutation. And then by replacing a random permutation with a pseudo-random permutation, we give a pseudo-random Simons function. Okay, as I said previously, for oracle separation, actually we don't really worry about the oracle is efficient, implementable or not. But it turns out the efficient separation can be used to give a two-prover verification, which is going to be the next part of this talk. So formally, we two-player protocols for separating C from D is if there exists two parameters C and S, which are called Completeness and Soundness, and classical verifier V, such that if the one of the players called PA, which is the target machine that we want to certify its quantum depth, if it runs in C, then there exists a pair of players who share entanglement with each other, such that the verifier accepts with probability at least C. On the other hand, if the player PA, the target machine PA, runs in D, then no pair of no players PO and PA would make the verifier accept except with some tiny probability S. So if the players are perfectly reliable, the corresponding two-player protocol will be very straightforward. So the idea is that we can have the prover PO to perform the oracle queries, and the PA to perform the unitary, but that is to perform the unitary between the queries in this picture. So in the protocol, we interleave the computation done by PO and PA, and then finally PA outputs a string, and the verifier checks whether the string is the hidden shift. But for soundness, we want to make sure that even the prover tries to cheat, it does not pass the protocol if PA doesn't have sufficiently large quantum depth. So to make sure the player follows the protocol honestly, so in particular, we rely on the protocol by broadband for verifying BQP languages. The protocol, the original protocol by broadband is a protocol for verifying BQP, where the verifier performs a fixed set of K-frame measurements. So suppose the verifier can perform K-frame measurements reliably. She showed that we can come up with an indistinguishable test for detecting bit flip and phase flip errors. But this original protocol is for BQP for decision problems. Turns out that we show that with modification, we show that there exists a protocol such that for efficient quantum, which certifies efficient quantum circuit C. Meaning that if the prover passes a protocol with sufficiently high probability, then it implements a quantum channel that is close to the target, the ideal quantum ideal computation C. So the idea is to modify the X test, the test that is done by given by broadband in a different way to show that the entire state, to detect whether the entire output state has error. And then to achieve purely classical verification, we must delegate the K-frame measurement to an untrusted quantum prover. So to get this, we apply the self-testing protocol by Colangelo, Grillo, Jeffrey, and Vivek. They show that there exists a two-player test called rigid, which certifies preferred measurements. Putting these ingredients together, we give the following protocol. So initially, the verifier checks a random query, I. For all but the ith query, the prover PO performs the oracle query O, and the prover PA performs the unitary between the queries. And for ith query, the verifier chooses a random test to certify that PO actually performs the oracle query. And then with some tiny probability 1/d, the verifier doesn't perform any check. Instead, it trusts the computation performed by PO and PA, and then accepts if the string output by PA is the hidden shift. So the last part is a protocol that certifies a single device that has a sufficient large quantum depth. So to get such a protocol, we rely on the cryptographic test of quantumness by Brzezinski, Cristiano, Madhav, Vazirani, and Vivek. They show that under a hardness assumption called the adaptive algorithmic property, they give a cryptographic test of quantumness. So what does the property say? It says that under quantum hardness of learning with errors, there exists a distribution over 2-to-1 functions f such that no quantum algorithm can output a tuple of three strings, y, x, and e, such that x is a preimage of y. And the E is orthogonal to the XOR of the two preimages. So we call X a preimage of Y, and E an equation that's associated with Y. But on the other hand, it is quantum efficient to get either YX or YE. So with these observations, they give a cryptographic test of quantumness. So initially, the verifier samples a function f. The prover samples a image y and send it to the verifier. After that, the verifier randomly chooses a challenge to ask the prover to output the image or equation. So by this property, it is simple to argue that there is a quantum prover who wins the protocol with probability 1. For the soundness, we want to show that for every device, every classical device can only succeed with probability bounded away from 1. So to show this, we show that if there exists a classical, they show that if there exists a classical device which passes the verification with high probability, then you can rewind such a prover to break the adaptive algorithmic property. And then more recently, two groups of people independently show that the evaluation of the function f can be done in constant f. So in this talk, we ask a question: can we distinguish a depth d plus constant from a depth d QC scheme? So in our paper, we show that we can do that. So the protocol is quite simple. It pretty much runs the first two steps of the protocol in the previous slide in parallel. And then after that, the verifier sequentially tests whether the prover can actually respond with preimages or equations. So for completeness, it suffices to give a D plus constant QC schemes for this protocol. So the idea is the following. Initially, it queries a function, which can be done in constant depth to prepare superposition of the preimages. And then the verifier sequentially asks the prover to answer to give preimages or equations. And the prover actually performs control holomark gates in each step to win the protocol with good probability. So for soundness, we show that no DQC scheme can succeed with probability that is bounded away from 1. Otherwise, we can break the adaptive probability property. The major distinction from the argument that's done in from the the paper by Brzezinski and others, is that we no longer have a proof of soundness against only a classical prover. So we must have a different argument that reduces from the adaptive probability. In summary, in this talk, I gave protocols that allows us to classically certify quantum depth. So in particular, the paper consists of 3 parts. The first, we give improved oracle separation between hybrid schemes that improves the existing oracle separation results. Then we show that the oracle can be made efficiently implementable, which the result turns out to be useful for the second part of our contribution, which is a 2-prover verification scheme. So in this setting, to certify the target machine has sufficient large quantum depth, we add another helper machine, which is also untrusted. And then they may share entanglement with each other, such that if the provers coordinates in a certain way, and the target machine has sufficient large quantum depth, then they pass a protocol with high probability. If the target machine doesn't have sufficient large quantum depth, then the verifier rejects with high probability. And then the last part of the paper was a single device protocol that extends the cryptographic test of quantumness to certify quantum classical hybrid schemes. So for future work, there are a couple of questions that remains to answer. First of all, can we give a separation between D+1 and depth D schemes? And then can we give a space-efficient protocol that runs on disk devices? So our protocols are not very space-efficient. So can we give a space-efficient protocols that allows a very small quantum device to win to pass a verification with good probability? So currently, we gave a protocol that the run complexity scales with the depth we want to certify. Can we give a constant run protocol for an arbitrary D which is polynomially bounded? Okay, so this ends my talk. Thanks.